start to model neuronal networks? Where to start? So, many years ago, people realized that if you take an electrode on the surface of a scalp and you see this spindle oscillation, so you see this motif oscillatory, transiently oscillatory, you see that it is associated with a behavior at a cellular level where you see that the membrane potential of the neurons is switching between a sort of low state to what is called an up state, where you see this discharge, firing discharge. First of all, at that time, it was a surprise that the voltage membrane of a neuron could be a different stage. Where it comes from? What you learn from the books, it's that the membrane potential is minus 60 millivolt, but it's not at minus 60 millivolt. It changes all the time, and there is some kind of rhythmic pattern which show that this is even more complex than what we think, but there is something deterministic to understand. Okay, so this was when more than 20 years ago, people realized that there was this change in this type of patterning, which is called up and down state. Again, you can see it here, different types, and you have the impression that you have something, a pattern that repeats itself. And the question is where that comes from. Is this intrinsic property of neurons, like neurons are made of channels, potassium channels, sodium channels, this is the basic of neuroscience, and more channels, or is this a consequence of the fact that this is inside a network, or both? That is, if a neuron is not in a network, it will not produce this. The network is the driving force for this behavior. That's the question. So what was also interesting, so when people started to look at it seriously and do quantification, they started to see that the membrane potential is not at minus 60 millivolts, but if you record the spontaneous activity of the neuron, you see that sometimes there's a shape between minus 70 and minus 50, but more important, there are two bumps. And these two bumps appeared when the evoked activity, when you stimulate, for example, you give a flash stimuli or sound stimulation, they also found that this was present. So this becomes important to understand why you have this. So you evoke a sound, you have some behavior where the neurons for hundreds of milliseconds will move on from its state to an upper state, and this could repeat itself. And then they look at the statistics of what happened, time in the up state, how long you stay in this state here, and start to look at the statistics basically. Okay, so this is a subject that we've been interested in over the last 20 years, and this is how we started really to go into modeling of neuronal activity. Yeah, so this is another example. You can have in the auditory cortex, in the barrel cortex, what people looked at, they say, all right, what is the probability or the time spent in up and down state? And they fit it for the duration, so you can imagine, you can quantify this. You look at the time you're in up state, the time you're in down state, you look at the histogram, and you fit. What do you learn by doing this? Is if the fitting has no derivation from a theory, you can just correlate your fit with extraction of parameters. And what I want to bring in here is that if you have a correct model, maybe you will do a different fit. You'll do a different fit. And that's what I want to discuss in the next class, which means now. So for this, we need to start the modeling. And the modeling starts with the physiology. And if we consider, we make an assumption here, is that what I just showed to you comes from synaptic property. The synapses are responsible for this behavior. If this is the case, so in science we start with hypothesis and then we move on to see where we're going. Then we have to understand what are the property of a synapse. And the property of the synapse can be summarized by this graph. A synapse is the connection between pre- and postsynaptic terminal, where vesicles are going to be released and neurotransmitters are moving from the pre to the post. And so what people have observed is this. If you stimulate the postsynaptic terminal, if you stimulate, the presynaptic terminal, so you send stimulation, you have a pipette here, and you send a stimulation, you stimulate the cell. When the cell is stimulated, you have this event. So you have every 20 milliseconds, you send a spike, spike, spike. What do you see in the postsynaptic terminal? What do you see? You see this. That is, for the first spike, you have a big response. But for the second spike, you have a smaller response. And so on, until you get something very little. But if you wait sufficiently long enough, then you recover. You still have a response which is much bigger than this one. So this is a characteristic you would like to extract and use this in a model to start modeling things at a neuronal network level. The second interesting result, so those are other experiments, so this is the pre and this is the post, it decays, and so you can build a model that allows you to do this. So I'll come back in a second. Now I need to show you a second event which is of importance, is that you can do the same experiments and the spike, instead of diminishing, will increase in the postsynaptic response. It will increase. This is called facilitation. And facilitation is an increase in the probability of vesicular release from the pool. That is, there are two opposite phenomena. One is synaptic depression. You send spike, and the response in the postsynaptic part decays. You are an opposite effect where you stimulate and the response will increase. And why is that? The hypothesis, which was made a long time ago, is that there is a calcium accumulation, that when you have calcium accumulation, it increases the probability of release. Okay, so now we started to how to integrate this phenomena into a model. So I'm going to describe now what is called a phenomenological model. In physics, from the time of Boltzmann, the way physics was understood is that if I want to describe microscopic law, I can go to the microscopic level, count how particles are hitting a wall, and calculate temperature. So you go from small to big. So here we're going to go at the neuronal level by integrating the property we just discussed, and we'll start, I'll do the case of this depression. So I need to have a variable that will count. Let's say if I said depression is the number of vesicles available that measure this availability. So if mu, for example, is a fraction, mu, let's call it, measure the state of the synapse. Yeah, so mu is the fraction, let's say to give it into a physiological context, is a fraction of ready releasable vesicles. So if mu is 1, it means they're all ready. If it's 0, then nobody is ready. And so the way to construct it is very phenomenological. So you say that if there is nothing, if there is no depression, I want between t and t plus delta t, let's say, to recover with an exponential rate. So if this is the case, I say between t and t plus delta t, I was mu of t, and if nothing happened, I want to recover, which means that, so mu of t plus, so what happened during t and t plus delta t, I said that I want to recover to 1 with a time scale tau. So if I put this, so I look at how many vesicles I have, and I said that during t and t plus delta t, there is more vesicles that are proportional to the difference between where I am 1 and mu. So that mu, if you put this in this way and you divide by delta t, mu of t is 1 minus mu divided by tau, and if you integrate this, right, you get something that goes exponentially to 1, right? Mu dot, so this is tau mu equals 1 of mu, so the solution, the steady state solution is mu equals 1. If mu equals 1, this is the solution, and then you converge exponentially to 1. So it's 1 minus or plus a constant exponential minus t divided by tau, right? And so when t goes to infinity is 1, and the a should depend on the where you are at a given moment of time. So this is minus a is a constant, and you converge to 1. Right, so for example, if at t equals 0, I have t equals 0, I have 1 minus a vesicles. So if at t equals 0 nothing happened, a equals 1, so you get 1 minus exponential t minus 2. So this is an exponentially converging rate to 1. That's to explain the first term here. Now, what happened between time t and t plus delta t if you stick an electrode and you stimulate? This is exactly the experiments that we just showed a slide ago. So if you stimulate, I showed to you that if you stimulate with a certain frequency, you get a decaying response. It will get smaller and smaller. So, well, in terms of vesicle, each time you have this, it means you release some vesicle and you have thus less vesicle that are available. So mu is here measuring the quantile of vesicle that are disappearing. Mu is the number of vesicles available at time t. So if, for example, you have 1 and it has decreases, now it's, let's say, at 0.5. And so, and finally, this is the rate at which you fire. So this is the rate and that we converted. There's a famous conversion. This is the rate of activation, right? So if I have 5 spike, you count 5 spike, you multiply by mu, and this is how much you're going to reduce the number of vesicles. And R of V has usually this shape. It's V minus a threshold plus. It's a function like this. You have a threshold before there's nothing, and then you can approximate this conversion from V to RV. Now it's a little bit more subtle. People have done it continuously. They show that has some effect. Fine. So this is a way to say that if the voltage of your system is high enough, it leads to, because it's depolarized enough, it leads to high frequency stimulation. Otherwise, if the potential is less than a certain threshold, then there is nothing, no stimulation. Plus means 0 if V minus T is negative, right? If V minus T is negative, V is 0. So this is 0, equal to 0. And when it is positive, it is equal to V minus T. That's what it means. Right? This is just this simple function. So this allows to connect the state of the synapse in terms of the number of vesicles available to be released to the voltage of your ensemble of neurons. Okay, so next is to find out an equation for the voltage of the ensemble of neurons. Yeah, so this we discussed. I explained to you the two cases. All right, so right now, I should have gone another sleep here. Okay, so now we've discussed today this equation. I explained to you exactly where this equation is coming from. The mu, t the rate, the time scale to recover, u is a fixed quantity, is a constant. And now I want to connect with the dynamics of the population of neurons. Alright, so I will do the same. I say if nothing happened to a neuron, the voltage of a neuron should come back to, so let's say that the steady state is 0, it should come back to the steady state exponentially fast, which is exactly what you get when you have the first component. The solution of v dot equals minus v tau is just exponential converging to 0, so v of t is a constant, whatever it is, exponential t divided by tau. And it converges to 0. This is what it means. However, if I have one neuron connected to another neuron, connected to many neurons, they connect and they can interact and have synapses. If I want to understand the dynamics of an ensemble of neurons sufficiently connected, I need to say that if all synapses are depressed, which means what for mu? Mu equal to 0, there is no synapse available, so it cannot communicate. So the communication is proportional to a weight, which is the number of connections. So this is related to the number of connections. This is the number of vesicles available, and this is the firing rate. If the ensemble can fire at a certain frequency, which is v minus t plus, which is just what I showed to you, then it is connected, it has a certain mean number of connection, and mu is the number of vesicles available, then v will change state. It will depart from 0 to a different value. Okay? So this is how we built at that time this very elementary model which has two variables, which means two equations, one for the number of vesicles and v for the mean voltage. And then we said possibly the system can have internal noise. So here you have noise on your system. Right? So you have noise, but you can also send an external stimulation of your ensemble of neurons, which is sufficiently connected. So what does this model assume? It assumes that each neuron has the same connectivity, the same number of connections, and it's well homogenized. So this is called a mean field model. This is called mean field model, which accounts for depression to understand how an ensemble of neurons sufficiently connected could behave. And so it took us some, once you write this type of model, you have to study it. What kind of behavior it has, and can this, for example, is this sufficient to recover this up and down state that I just explained to you? Okay, so this is what we have been interested in, and the first thing to do is to is to study what is called the phase space. what is the phase space? So the phase space is how the system behave in mu and v. So mu can vary between 0 and 1. That's mu. And v vary in here. So I don't care about noise, I don't care about this, and I want to understand what are the point of the stable point. So the stable points are given because we know that everything will occur around those points is where v dots equals 0 and mu dots equals 0. So for example, if you take the point mu equals 1, if mu equals 1 and v equals, for example, 0, or v equals t, let's say v equals 0. If v equals 0, you agree that mu equals 1, v minus t minus is negative, I'm going to take the positive component, so this is 0, this is 0, this is v equals 0, this is 0, mu equals 1, but v equals 0, so this is 0. So this is a stable point. Mu equals 1, v equals 0. So I have a stable point. Are there other stable points? Well, to get the other stable point, you need to look at the solution of this equation. So let's do it in here. So you have v minus v plus, so suppose this is positive, so v is bigger than t, it's mu omega v minus t equals 0. So from this I'm going to extract mu. So mu is equal to what? So this is v divided by v minus t. Is this what I want to do? I want to extract v. Yeah, sorry. I want to extract v, not mu. So I want to extract v. So I have minus 1 plus mu mu omega v, right, equals t mu omega, which means v equals t mu omega divided by minus 1 plus mu omega. You agree? Great. So now I'm going to replace this in this equation. So I have 1 minus mu t or minus mu u, and I need to calculate v minus t plus. So what is v minus t? V minus t is this minus t, right? Is this correct? V minus t, so this is t mu w minus, there's a mistake. V is minus 1 plus this equals t, right? And this is minus 1, and v minus t is what? T mu w minus t, so minus and minus is plus, so minus 1 plus mu omega minus t, so minus t is minus and minus is plus t minus mu omega t. You agree? So this and this goes and it remains t. So here I have to do 1 minus this mu, and this is t divided by minus 1 plus mu omega equal 0. You agree? Alright, so if I now multiply by whatever it is needed, I get 1 minus mu multiplied by minus 1 plus mu omega minus tr u mu t equals 0. So what does it mean in terms of mu? I have mu minus mu squared omega then I have the term in mu. So where I have mu coming from 1, minus and minus is 1, and I have a mu coming from here, plus omega. Right? And I have a minus 1 term that I need to add to this. So plus tr u, no. There is a mu here, right? Yes. So I need to add, there's a minus 1, and there's a term here which is what? It's minus tr ut. You check if I'm doing a mistake, and then there is a minus 1, it's a minus 1 equals 0, which means plus, plus, and plus. You agree? I didn't make any mistake. This means that if it's back to what you learned at school, if this is second order equation, how many solutions do you have for mu? We have 2. So we have mu plus and mu minus that you can calculate. By calculating, you have to calculate the discriminant, 1 plus omega squared, 1 plus omega plus tr plus tr ut squared minus 4 omega. If this is positive, then you have 2 solutions which are given by mu plus minus equals what? So this is equal to minus this term, minus 1 plus omega plus tau r ut plus minus square root of delta divided by 2a, which is 2 omega. You agree? Okay. So, which means that you have 2 more points, and you have to position those points. Now I'm going to do something that you should do at home. There is one more thing you should calculate. It's to understand whether those points are attractor, repulsor, or saddle. So for this, if you have a dynamical system, x dot equals a of x, right? So I have a nonlinear dynamical system. I want to know if all the trajectories are going to be attracted here or repelled. So I need to calculate, so you do your approximation at this point, so let's call it A, B, and C, those points. And I need to calculate the Jacobian of A at those points, right? So I know that for each of those points, A equals 0, because by definition, this was when I calculated them. So near, let's say one of them, A, B, or C, I have to calculate x dot, so A of those points are 0, so I need to calculate the first derivative, which is dA, which is called the Jacobian, and do a little perturbation, so I call it y, and this little perturbation, so this is called the Jacobian matrix, and according to the eigenvalue of this, in dimension 2, I know everything. So the matrix can be written in the form of lambda plus minus I omega, or minus lambda plus minus I omega, and I need to check whether lambda is positive, 0, negative. If this is an eigenvalue which is complex, the eigenvalue can be, one can be positive and the other can be negative, like lambda 1, lambda 2, or the two be positive, lambda 1 positive, lambda 2 positive. This is what is called a repulsor, this is called a saddle, and if they are all negative, for example, I have lambda and lambda, this is called an attractor, right? So this is known, I mean, this is the classic, this is an attractor. This is called a saddle. One is negative, the other is positive. And this is called a repulsor. Okay, so to finish, let's go back to, now that we understand how to do this. This should be done at home. We have 3 points. So you can calculate the eigenvalues by, you take the point I just showed to you, you do the expansion for the point mu equals 1, v equals 0. So we have to do a Taylor expansion on this and calculate the eigenvalues in the 2 coordinates, and we do the same for the 2 other points. So I'm going to show you what we get. We got 1 point here and another point here. It turned out, after some calculation, that this point is a saddle point. A saddle means trajectories are leaving this way and are entering that way. Right? There is one direction where the eigenvalue is negative, which means if you start here, you converge exponentially. You know, if x1 equals minus lambda x1, you converge exponentially with lambda, rate lambda, to this point. But if lambda is positive, you diverge. So that's locally what happened. It turned out that this point here is an attractor in a saddle point. It's something that does something like this. It attracts. And the difficulty, I mean, this was what people work on for the last 70 years. What are the trajectory? What is the phase space? How the trajectory looks like. So, since the trajectory cannot, in dimension 2, they cannot cross each other, the analysis goes like this. All trajectories that are here will be attracted, because this is an attractor, to this point. Here it turned out that there is what is called a limit cycle. Okay, this is something that there is a limit cycle. There is a limit cycle, which is there is a circle. A circle is solution. And when you go this way, you make a loop, and you can come back this way, and this goes and rotates in the opposite direction. And with this allows to have what's called the phase space. You have an attractor here. And so now you understand that the system of equations has 2 interesting features. There are 2 attractors. Either the dynamics is attracted here, and suppose you have a little, so if there is no noise, if you start here, what happened? You go to 0. If you start here, what happened? You oscillate, and you start here, that's it. You end up at this point, and nothing happened. But if you have noise, what happened? That's right. So now let's go slowly. Now we have an interesting picture. If you have noise, if the noise is small enough, you are going to converge here, stay a long time, and you have a chance to cross this part. If you cross this part, because the force is so strong after this, you are going to make a huge turn. Come back here, and you go back, and then you have noise again. And you can repeat. And what can happen also? You can go here, you move, you go to this direction, and for some reason here there's a little bit of noise that will push you here. The noise pushes you here, you are going to fall into the attractor.
Did you say that it turns in the opposite direction? Or no?
Whatever the direction, it should turn the right direction. If I put the other way, you should put it the way. Yeah, it should turn in the right direction. So if it can this way, no, I think it's good. It turned this way. But then the noise can make the system move outside the attractor, and suddenly you'll have a structure. You'll go back to the deterministic system that will push you back to here. Now this is interesting. It's interesting because you can learn many things out of this. We learn that the noise gives you a sort of bistability behavior, and this is derived from synaptic depression alone. You learn that if you are in this up state, you are going to oscillate with a frequency which is associated with the imaginary part of the eigenvalue. So I wanted to do it by hand, because if I show you the result, it will come out of the blue. But now I showed you how to construct this, and this is what you have to do usually in dynamical system. In dimension 2 it's much more complicated, that's why I didn't go into this, but in dimension 2 this is what you get. So this is exactly what you have. What I showed you, you have a trajectory, this is by hand, and this is a real simulation. The real simulation shows something that is very, very sharp. You move on, so this is this region here, and you can escape here, and you see the deterministic behavior. And sometimes, most of the time, you enter here, then you are going to oscillate. You oscillate around it until you go back, and then you continue. And that's the behavior. Yeah, so what we discover is more than this. So this is again the system as I just described. We already discussed each term. And an additional subtlety, it took us years to understand this. It didn't come for free. We realized that the attractor here is very close to the boundary. So what do you think? So first of all, now we can give a good interpretation. You are in the down state, there is this burst, the fact that you have to do this big loop. Because of this, there's a sort of burst population. And then you enter into this. In the up state, you move, and you see that there is here some frequency. And this is associated actually to a frequency of oscillation, which could be, at that time, what we found out, it could be of the order of the alpha band, which gives us the idea of the Hofstein-Uhlenbeck process. It took us 15 years to move into all of this direction. And then, by noise, by fluctuation, it goes back to the down state. And the down state is associated to the lower attractor. And then what we discovered is something very interesting. First of all, when we look at the distribution of time in the up state, we didn't find a Poissonian behavior. Poissonian is, everybody assumes Poisson. It is the time, it's exponentially long, exponentially decaying with respect to time, the time in the up state. But no, we didn't find this. So what is very specific to this, to calculate the time in the up state? In other words, how long do you stay in this attractor? Well, if you are blocked here, you are going to rotate, but because it's very close to the border, what we understood is that each time you loop, you can escape. But if you miss the point where you can escape, you have to loop. Which means that in some sense, you don't expect the particle to escape at any moment of time. There was some kind of quantification of the time the particle, the imaginary particle that represents the state of the membrane, stay in the up state. And when we look at it more specifically, this is exactly what we found. We found that the time in the up state, there are peaks, and at some point when it's sufficiently long, everything starts to be intermingled, and you have something that decays. But this was associated to the rotation number, the winding number around the attractor. So now if you have this, are you going to fit a Gaussian or any decaying on your statistics, the answer is you have to revise the way you see your data. And that's at some point, yeah, so this is to explain, the story, what we found out here, the region of escape was very small, very sharp, and either there is a rotation, one rotation, two rotation, or three rotation, and this was quantifying this event that I showed to you. Okay. Yes, and then we said, all right, now we have to go back to the data. And this we did, so this started 2005, we published 2006, we went back to this problem in 2010, we published this in 2015, and then we started to use all of this in 2020 to use this model to start to do modeling between population of neurons during anesthesia. It's about 20 years. So if you extract the time in this upstate, what we found out is if the model was correct, the Gaussian fit or any fit didn't mean anything. And that's, so people say they could not get, and even when you do simulation, you cannot get a proper decay. There was this peak. And we started to say, no, this peak, they have a meaning. This is the first peak, this is the second peak. This is exactly what you get from the distribution that you have to fit because of the peak. It's not Poissonian. It's a sum of a Poissonian distribution plus an exponential with cosine. And cosine has to do with what I just described to you. And so we said at that time that there is a peak of interest, and the reason for this is the model that we have, and it makes sense. And from this peak, you can actually extract this omega and understand more about the underlying synaptic property that generate up and down state. Yeah, and so finally we had these peaks that we extracted, and at that time we quantified. We showed that there was no the solution with the sum of exponential with cosine was much more appropriate, especially to account for the first peak. We could account for 1, 2, 3, the first 3 peaks, which was good because it's what we said. After 3 peaks, then it should vanish, and this is what we did at that time on these two types of data: auditory cortex and barrel cortex. Yeah. So okay, this is to show you, and I think I will stop here. I'll see if I go next week about adding one variable, which will make everything more difficult because then you move on to 3 dimensions. But so I know that machine learning is predicting with no model, at least not of this physiological model. But what we think is that the still physiological model not only allows you to predict, but to understand. Do you need to understand to predict? That's another concept. Maybe you don't need to understand to predict. And this is what happened. I think that at least if you want to understand, it brings better insight of how the system works. And we cannot afford just to ignore the understanding part. Understanding is part of the process that allows to have prediction and better prediction. I'll stop here. Next year, 2025, we'll continue on this. We'll move on, we'll continue on this understanding how you model neuronal networks. And then we'll move on to neuron-astrocyte interactions.